So please stay and I wish to encourage your comment or discussion. Now, okay, the first speaker in this session is that Dr. Yokokawa, who is from the Riken, Japan, and he is the key person of the art simulator to develop very efficient code and machine, and they also currently are the key person of the next generation powerful machine in Japan. So let's have a his talk.
Okay, thank you, Chairman. And it's my pleasure to give a talk here, and it's my honor to invite me to this workshop, Newton Institute, Cambridge. And first of all, I'd like to talk about a little bit why I make a presentation here first. So I had an experience of developing the Earth simulator maybe 7 years ago. Dr. Zakaria mentioned that the Earth simulator is 40 teraflops vector type distributed memory supercomputer system. At that time, I worked at JERI, Japan Atomic Energy Research Institute, and then we made the Earth simulator by the national project. And at that time, a simulation code for box turbulence flow was used in the final adjustment of the system with Professor Kaneda and the Professor Ishihara. And on that machine, I made a large simulation of box turbulence flow with the spectral method was carried out. And now I changed the job, and I am engaged in a petaflops supercomputer project in Riken, the Institute of Physical and Chemical Research. So today in my talk, first I will talk about simulations on the Earth simulator, turbulent simulation with the spectral method on the Earth simulator, and next, and then I would like to talk about a little bit the Japanese petascale supercomputer project, and then I will mention some trends of the HPC system, and finally I summarize my talk. This picture shows you the Earth simulator system. It was completed in 2002, and it achieved 35.86 teraflops sustained in Limpak benchmark in a total whole system with the whole system. And the blue cabinet shows a compute node. It composed of the 120 cabinets, and in the center of the picture you can see the right blue cabinet. It is actually a network cabinet. So the features of the Earth simulator is a vector machine, and also the compute node is connected by the full crossbar network. So each node can communicate with the other compute node by one hop communication. So it is very our simulator can have a high-speed network communication among the compute nodes. That's a main feature of the Earth simulator. And this machine was also chosen as one of the 2002 best inventions by Journal Time. Okay, so why I did the spectral simulation on the Earth simulator, I would like to explain on that things. In development of the hardware system, I think it is important to make performance evaluation of the system, especially in this case, the Earth simulator at the final adjustment phase. So it requires some kinds of application software to check the computational performance or some kind of communication between the compute node. So we try to find out some suitable codes to evaluate performance of vector processor, to measure performance auto communication among compute nodes through a full crossbar switch, and to make an operation of the Earth simulator stable. So we have several candidates to do this. One is the LIMPAC benchmark. LIMPAC benchmark is a solver of the large-scale linear system, and by the calculation, you know, the top 500 list. It list shows how fast the LIMPAC benchmark solved. So, but the LIMPAC benchmark is just a solver, not make any scientific achievement. And then I think about the atmospheric general circulation model, because the Earth simulator, one of the purposes of developing the Earth simulator is that AGCM carry out. But the conventional atmospheric general circulation model is so many program lines and so big. I think it is difficult to tune this code to the Earth simulator so fast in time until the Earth simulator was completed. So I quit to use the atmospheric general circulation model either. So we think about is there any other code to do this performance evaluation of the Earth simulator. So I think the spectral turbulence simulation code is suitable for this purposes because it has the intensive computational kernel and a lot of data communications. In this case, I mean that the spectral turbulence simulation code is used the FFT, fast Fourier transforms. So it requires a lot of communications among the compute nodes. And also, it is very simple code. Simple means the little statement of the program and very understandable for the structure of the code. And also, this code is very significant to computational science because the turbulent flow is one of the grand challenges computational science and high performance computing, I think. So I used the spectral turbulence flow code to check the estimator performance, and we made a new spectral code for the estimator for maybe we spent 2 or 3 years to make this code. And the feature of this code is written in this list. For the spatial discretization, we use the Fourier spectral method, and in the method, more truncation and phase shift techniques is used for the aliasing error in calculating nonlinear terms. And also to keep the precision of the calculation, fourth order Runge-Kutta method for time integration is used. In the implementation of the code on the Earth simulator, there are some points of coding. One is it must be optimized to the Earth simulator. It needs a coordinated assignment of calculation to 3-level parallelism. The Earth simulator has the 3-level parallelism. One is vector processing. The other one is microtasking. The rest one is the MPI parallelization. So we use these 3-level parallelization for the code. And also to keep the byte per flop. Byte per flop means the data transfer rate between CPU and the memories versus operation performance. This value keeps to small. So we use the higher radix F50 in the code. And we check the code carefully and precisely redundant process or redundant statements of the code and the redundant variable was removed. So this is this optimization makes us possible for the large-scale turbulence simulation. This is an example of the data of the calculation for one-time step of the code. The vertical axis means shows the world time, and the horizontal axis shows the number of compute nodes. So when we simulated for the 2048 cube simulation with the 512 compute node, it takes 3.21 seconds for one-time step simulation. And also we obtained 30.7 seconds for the 4096 cubed simulation on the 512 compute nodes. And it took 3 days with the 512 compute nodes to complete the reasonable time of simulation. This is the performance of the code. When in the 2048 cubed simulations, with the 512 compute nodes, we obtained the 16 teraflops sustained performance. It means the 50% of the peak. This value cannot be obtained for the PC cluster or something like that on the recent used supercomputer. So it's an amazing value to get this sustained performance. And this graph shows the achievement of the box turbulent flow simulations. We made the largest simulation in 2002 on the Earth simulator with the Professor Kaneda and Ishihara. And we got a Golden Bell Prize in SC 2002 by this achievement. And next, I would like to talk about the Japanese petascale supercomputer project. We call this project the Next Generation Supercomputer Project. And the objectives of the project are to develop the world's most advanced and high-performance supercomputer, and to develop and deploy its usage technologies as well as application software. And this is assumed one of Japan's key technology of national importance, which was made by the Council of Science and Technology Policy of government. So this is a very important project in Japan. The development period of the project is from fiscal year 2006 to fiscal year 2012, and the budget is almost $1 billion US. But this is expected value because we are now talking with the Ministry of Finance to get this amount of the budget. So we are now talking with them. And also RIKEN is a national institute in Japan for the physical and chemical research. Plays the central role of the project in developing the supercomputer and under the law. The government make the law to encourage this project. So in the law, the RIKEN was designated to the main role. The goals of the project is following 3 items. Firstly, one is the development and installation of the most advanced high-performance supercomputer system with Limperk performance of 10 petaflops. The second one is the development and deployment of application software, which should be made to attain the system maximum capability in various science and engineering fields. The last one is the establishment of an advanced computing science and technology center as one of the center of excellence of research, personal development, and training built around the supercomputer. The major applications of the project is a wide range of fields, from engineering, aerospace, nuclear power plant, and so on. Especially the nanotechnology and life science is assumed to a grand challenge research field, and some amount of money gives this field to promote making the application software. The conference, we are now doing a detailed design of the system. So today I would like I can say only this say only this figure for the system. This the next generation supercomputer will be a hybrid general purpose supercomputer, which provides the optimum computing environment for a wide range of simulations. This system it will be composed of the scalar unit and vector unit, and each unit are connected by the front-end unit. And also, those two units share the parallel file system, and each unit can access the shared file system to get files or save the result on the shared file system. And calculation will be performed in processing unit that are suitable for the particular simulation. And also, this parallel processing in a hybrid configuration of scalar and vector units will make larger and more complex simulation possible. This is a roadmap of the project. The project is a 7-year project. We are now in a detailed design of the system. That design will fixed next year. At that time, I can say a little bit more the system in detail. And also, we are now making a building in which the next generation supercomputer will house. The location of the supercomputer site is in Kobe City. Kobe City is apart from the Tokyo by 450 kilometers west, almost 280 miles. And this picture shows you the location of the site. There are Kobe Airport near the site, and we can access from the Tokyo by Shinkansen, bullet train, and from the Sannomiya station, it takes 12 minutes by Port Liner monorail. The Port Island is an artificial island, so there is a little resident area. So we have decided to set the supercomputer here. This picture shows you the artist's image of the building, and it has 6 stories, and in the right picture, you can see the rectangular shape of the in the finger. That is a computer building. So the research rooms are surrounding the computer rooms. So this is the photos of the site. There is it is under construction. So now we can not see any shape of the building, but it will be finished in 2010. So at that time, I have to move there. Anyway, so now I change the topics. I would like to talk about the trend of the HP systems. Almost the trend Dr. Zakaria have already talked, but from my point of view, I would like to try to mention. So this figure shows you the aggregated system performance, increasing rate of the aggregated system performance, and also a single CPU performance. This figure shows you also a CPU frequency rate on the same figures. You can see the CPU frequency is gradually increased in this figure. But recent research that CPU frequency will head to the limit because of the limit of the silicon chip technology. With this limitation, the single CPU performance is also limited. Will also limit. But the aggregate system performance is getting higher and higher because this comes from the parallelism of the system. There are many computing nodes on the system, so if the single CPU performance is limited, the amount of the aggregated system performance can make higher and higher. So the HP system will have the large number of processors, around 1 million core or more in 5 or 10 years. And each chip will be a multi-core system. Multi-core means there are several CPU on one chip, one die. And also it will be many core which has more than 64 CPUs in a processor. Therefore, each core has a low performance, and also each core has a small main memory capacity, like the cell special processors. If we use this CPU, fine-grained parallelism is necessary to think about. And also, each processor consumes raw energy, which means low power processors. But to lower the power of the processor, we have to take the narrow bandwidth between CPU and main memory. Because of the there is a bottleneck of the number of signal pin on the one CPU, and also to decrease the electricity, we have to decrease the line between the signal line between the CPU and memory, main memory. So those processors have the narrow bandwidth between CPU and main memory. And also bisectional bandwidth among compute nodes will be narrow because the one-to-one connection is very expensive and power consuming. Altimeter has the full crossbar switch. Full crossbar means every node can connect the every node. So that architecture is very expensive. So to the future HP system, it must be narrow bisectional bandwidth system. And this figure also shows power per floating point performance. This line is the normal decrease of the power per performance. It was almost a 1/10 decrease in 7 or 8 years. But the recent Brugin nail is here. The gap between the altimeter and Brugin nail is almost 10 times we have. So the Brugin nail is on the trend of recent HP systems. It has a small performance, low performance processor and the low byte per flop rate. So in the near future, this Brugin's trend is followed for the HP system, I think. So such a trend gives the very important impact to the spectral simulations. In any case, the HP system can have a high performance in impact benchmark. Any computer system has the almost 70 or 80% of the peak in the impact benchmark. And because the more the number of processors is higher the impact performance. So it is not necessary that impact performance denote real-world application performance, I think, especially the spectral turbulent flow simulations. Small memory capacity for each processor of the future HP system forced us make a fine-grained decomposition of space, and we have to take increasing communication cost among parallel compute nodes. And also narrow memory bandwidth and narrow inter-node bisectional bandwidth forced us the memory wall problem and low all-to-all communication performance. So we need any algorithm with the low byte per flop in place of the FFT in carrying out the spectral simulation. So this trend does not completely fit during 3D FFT, I think. Especially the box turbulence simulation are getting to be difficult to perform during the reasonable simulation time. So we can use more and more computation resource in near future on the recent trends of recent trend HPC system. But final resolution simulation by spectral methods needs a long time calculation because of extremely slow of communication among parallel compute nodes. And we might not be able to obtain the final cost in reasonable time. I'm not sure, but it might be. This is the estimate value of the when we carry out the more than 4,096 cube simulation. If simulation performance with the 500 teraflops sustained on the machine, 8,192 cube simulation needs the 7 seconds for one time step and 100 terabyte total memory, and it takes 8 days for 100,000 steps and 1 petabyte for complete simulation. And also 1638 for cube simulation needs 1 minute for one time step and the 800 terabyte total memory, and 3 months takes to complete the simulation. In summary, so I would like to summarize my talk. Spectral method is very useful algorithm to evaluate the HP system, I think. So in this sense, the trend of H system architecture is going to worse. Even if peak performance of the system is so high, we cannot expect high sustained performance. And it may take a long time to finish your simulation due to very slow data transfer between nodes. And I would like to ask all of them, can we discuss spectral method and change the algorithm? Or we have to put strong pressure on the computer architect or architecture community and think of any international collaboration for developing the supercomputer system over the world, which fits the turbulence study. I usually think about the HP system as a particle accelerator like CERN. So finally, I would like to ask a question. So I want to make a simulation on a new next generation supercomputer developed in Japan. So I would like to ask you, up to what size of box turbulence simulation should we carry out? So thank you for your attention.
So this talk is very impressive, or maybe give me some impression of the blessing in the future as people who are involved in FFT business. But his talk contains a very important message to the community of the turbulence. Probably you have many questions or comments.
I would like to ask a question about the possibility. Are you planning to use again the spectral code at the beginning to test your new supercomputer?
I want. But this time the next generation supercomputer is open to the wide variety of application area. So there are some evaluation process to use the supercomputer. So I will apply to get the CPU time to use in next simulation. Even I am developing the system.
A question and a comment. The question is, when you put there the architecture of the system that you are developing, your petaflop machine, there was a big chunk that was a vector processor. But when you started speaking about the computer architecture, that was gone. You didn't speak about vector processor. Are you thinking of having big coprocessors, or is that?
Yeah, even the vector processor, we have to think about the low power and the number of processors to gather into the system. Maybe even the vector processor, we have to follow a little bit. We have to follow a little bit to the trend of the HP system. So I think we cannot obtain the same performance as the Earth simulator, as the same performance as the Earth simulator. Even the vector processor, I worried about how performance we obtained.
Okay, then I had a comment. When you had your estimates of the time that it will take to do the box, you had there a number of steps.
Yeah.
The number of steps goes with the size of the grid. If you double the grid, you have to double the number of steps. Don't go from 100,000 to 125. You go at least from 100,000 to 200. Otherwise, it's not.
Yeah, that's a good question. But I am in a computer science area, so I extrapolate the previous time steps. So I have to ask the Kaneda sensei or Ishihara sensei to determine these steps. Anyway.
You have to go with the grid.
Of course, you know that our community, we are very keen of your success because if you, maintaining the vector possibility is quite essential to, this community, of course, but also I think atmospheric science and the people dealing with continuous medium and even plasma physics, which are going to have huge issue in terms of, ITER and all that development. And the trend, from what we see on the other countries, they go to this very tiny parallel computers. So that's just a general comment. So we really hope you succeed. And
I hope.
But then quite recently, I went to some announcement where I've been extremely impressed, and I want to confirm maybe from our American colleagues too, that Intel has announced a chip which is going to be 80 core on just the chip. And I just say things by memory, like 1.4, 1.2 tera. The chip is more than a tera. Flop, and the consumption announced is 64 watts. 64 watts is really impressive. Watt? 64 watts. I can give you the website where you can have all the
I think that is reasonable.
Sorry?
I think its value is reasonable.
But you think this is, and I think they will have it within, it exists as prototype, but it will be on the market within 3 years. And that's also, you have this kind of pressure of what is available at the chip level. And so I'm really interested to have some comment about this trend is going to develop well or not. Because what you are announcing in terms of number of, core on a chip was like 32. But it seems they are kind of getting higher.
In the 5 years later, it will be 8 or 16 cores on a chip. But the many computer architects think about the many cores for the future. So if we make an exaflops machine, the CPU must be a many core system.
Okay, well,
so if I can expand
comment
on it. So we have a lot of experience with vector as well as scalar processors. And I'm trying to be somewhat careful because some of these things are non-disclosure agreements that we have. I don't believe, so let's step back and say, it is not vector that you are looking for, even though vectors could be nice. Vectors is just a way of organizing. What you want is more powerful processors, right? I mean, so that you can, you don't have to have so many threads.
Well, the nature of our problem, especially when you deal with incompressible flow, we can reconsider those hypotheses. But
Sure.
today we have a box of incompressible flow, which could be the whole atmosphere. And that means something. That means there is some very long connection in the physics of it.
Yeah, but I mean,
And because of that, we are kind of stuck, and vector is a kind of natural object.
so
Or
vectors
maybe
will.
tensor if you want, but I would love some tensor too, but not kind of very.
Okay, so we have some time after the so let's try.
Yeah, that's maybe for the next discussion. You're very right.